Chapter 1, Section 5, Digging Deeper, Building Features on Earth's Surface, Oceanic Convergent Plate Boundaries. At a convergent plate boundary, two plates are moving toward each other. Your common sense might tell you that one of them has to go under the other. One plate stays at the surface and the other plate dives down beneath it at some angle. As you have already learned, this process is called subduction. In some places, two oceanic lithospheric plates are converging. Figure 1 shows two cross-sections of subduction zones. Look at the lower part of Figure 1. There are good examples of these along the western edge of the Pacific Ocean. Look back at the world map of the lithospheric plates from the previous section. The Pacific Plate and the Indo-Australian Plate are moving toward one another. Oh, that's why this looks weird. Let me zoom in. There we go. Okay, so I'm just going to scroll down a little bit. The Pacific Plate and the Indo-Australian Plate are moving toward one another in the South Pacific. The Pacific Plate and the Philippine Plate are moving toward one another in the Western Pacific. Other subduction zones are located at the edges of continents. Here, collision takes place between a lithospheric plate with oceanic crust and lithospheric plate with continental crust. Look at the upper part of Figure 1. Okay, so they're asking you to look at the upper part here. In places like this, the downward moving plate is always oceanic lithosphere. The plate that remains at the surface is always continental lithosphere. All right, so they're saying oceanic lithosphere, continental lithosphere. All right, now what does it say? Okay, that is because the continental lithosphere is less dense than the oceanic lithosphere. Than the oceanic lithosphere. The west coast of South America is a good example. This is where the Nazca Plate and the South American Plate are converging. Okay, so it's saying, let me zoom out so we can see this. Figure 1, cross-sections of subduction zones. The lower cross-section, which is this, the lower cross-section shows subduction of an oceanic lithospheric plate beneath another oceanic lithospheric plate, which is ocean-to-ocean convergence. The upper cross-section, which is this, shows subduction of an oceanic lithospheric plate beneath a continental lithospheric plate or oceanic continent convergence. So this is ocean-to-ocean convergence, and this is ocean-to-continent convergence. I can zoom in now because we're back on this. All right, oceanic trenches. Look at Figure 1 again. All right, let me zoom out. Let me zoom out. They want us to look at Figure 1. Oh boy, I might have to go to 100%. All right, look at Figure 1. You can also just screenshot this and put this on a separate window. Let me go to 140. Can I do 140? I'll go 100. All right. Notice where an oceanic plate is subducted under another plate. The oceanic plate bends downward as it enters the subduction zone. The valley that is formed above the zone of bending is called a trench. Oceanic trenches are very deep. Many are deeper than 10,000 meters. This is twice the average depth of the deep ocean. The word valley is a bit misleading because trenches are wide and their side slopes are not very steep. You can easily spot the locations of trenches in most world atlases. They are shown with the darkest blue shading on maps of the world's oceans. Trenches are common in many places in the western Pacific where there is ocean to ocean subduction. There is a long trench along the west coast of South America. It is where the Nazca Plate is being subducted under the continent. Volcanoes at plate boundaries. You already know, let me go to zoom in so it can be easier read. Volcanoes at plate boundaries. You already know that volcanoes are common along mid-ocean ridges. This is where basalt magma rises up from the asthenosphere to form new oceanic crust. Volcanoes are also common along subduction zones. With ocean-to-ocean subduction, magma rises up to the ocean floor. A chain of volcanic islands called a volcanic island arc is formed. Ocean-continent subduction is similar in many ways to ocean subduction. However, the volcanic arc is built at the edge of the continent rather than in the ocean. The Andes mountain range in western South America is an example of a continental volcanic arc. A volcanic arc begins at a depth of 200 to 300 kilometers. At this depth, magma is produced above the subducted plate. It rises toward the surface because it is less dense than the surrounding rock. At first, it was thought that the magma was produced as rock near the top of the downward moving plate was heated by friction. However, geologists are now convinced that the melting is for a different reason. When the oceanic crust is first produced at the mid-ocean ridges, a lot of water is combined with certain minerals in the igneous rocks. As the pressure and temperature increase down the subduction zone, this water is driven off and rises upward from the plate. It is known that the melting temperature of the mantle rock above the plate is lowered when water is added to it. This causes some of the mantle rock to melt. This is a good way to explain why melting does not start until the plate has reached a certain depth of the subduction zone, and then stops at a slightly deeper depth. This melting at subduction zones all around the Pacific causes the Ring of Fire. Hydrothermal vents. There are places on the ocean floor where very hot mineral-rich water exists from cracks in Earth's crust. They are known as hydrothermal vents. Most are found in the Pacific and Atlantic Oceans. They are at an average depth of about 2,100 meters below the ocean surface. They are most abundant in areas of seafloor spreading along mid-ocean ridges. As plates move apart, cracks are created in the ocean floor. Ocean water seeps into these openings. The water is heated by magma. Hydrothermal waters are geologically important. They are able to contain minerals in solution as well as alter the rocks they contact. The heated water rises and follows a path back out into the ocean through an opening in the seafloor. Rapidly emerging water has little time to lose heat. Its temperature may be as high as 400 degrees Celsius. The minerals dissolved in the water form chimneys around the vents. Black smokers are the hottest type of hydrothermal vents. They emit what appears to be black smoke. However, it is actually minerals containing iron and sulfur. So right here. Hydrothermal vents are interesting to scientists for several reasons. They are believed to play an important role in the chemistry of the oceans. They supply chemicals to ocean water. While most of the deep ocean contains little life, many different types of organisms exist around the vents. These living things fascinate scientists. They are the only organisms on Earth whose immediate energy source is not sunlight. Instead, they get their energy from different chemicals in the water gushing out of a vent. These organisms include bacteria, tube worms, huge clams, and eyeless shrimp. So figure 2, let's look at figure 2. Hot mineral rich water flows out of the hydrothermal vents on the ocean floor. Okay. On the deep ocean floor. Hot spots. Not all volcanoes are associated with mid-ocean ridges and subduction zones. Hot spots, which originate at the boundary between the mantle and the outer core, are narrow plumes of unusually hot mantle material. These plumes rise up through the mantle. They melt the rock at the base of the lithosphere, creating pools of magma. This magma then rises to the surface, resulting in hotspot volcanoes. Some hotspots are located under continents. The hotspot producing the hot springs at Yellowstone is an example. At Yellowstone National Park is an example. See figure 3. Okay, so let's see what figure 3 is. So this is a hotspot underlying the hot springs at Yellowstone National Park. Let me go back up to where we were. One theory suggests that a bulge created by a hotspot may initiate the rifting of a continent. It is thought that a hotspot lies below the Great Rift Valley of Africa. This hotspot is responsible for this valley. There is also evidence suggesting that the New Madrid Fault may represent an aborted rift zone originally created by a series of hotspots. This fault runs down the Mississippi River Valley. So we're not too far from that. That's just west of us. Okay, let's see. The largest series of earthquakes in the United States outside of Alaska occurred on the New Madrid Fault. They took place in the early 19th century. That wasn't that long ago. That was the early 1800s. The earthquakes actually were responsible for ringing bells as far away as Philadelphia. They also caused the Mississippi River to run backward for a short time. In this way, plate tectonics can even affect areas that are within the heart of a continent. Growth of continents at subduction zones. As an oceanic plate moves from a mid-ocean ridge to a subduction zone, oceanic sediment is deposited on the top of the plate. The depth of the sediment can be as much as 100 meters or more. At the subduction zone, this sediment is scraped off. It is then added to the edge of the other plate. This material is deformed into very complicated structures and is turned into rock by heat and pressure. It becomes a solid part of the other plate. When material is added to the edge of a continent in this way, the continent grows larger at its edge. Continents also grow as the igneous rock of volcanoes and batholiths are added to the continent above the subduction zone. Batholiths are large masses of igneous rock formed when magma intrudes and solidifies. The growth of a continent along its edge in these ways is called continental accretion. This has been going on through geologic time. The continents have been growing larger and larger. Where are we? Let me scroll up a little bit. Larger and larger. Okay, so here we are. Continental convergent plate boundaries. The third kind of convergent boundary occurs where two continental lithospheric plates have collided with each other. What happens when a spreading ridge arrives at a subduction zone? The spreading ridge goes down the subduction zone, never to be seen again. After a spreading ridge disappears, the plate that was on the other side of the spreading ridge is consumed down to the subduction zone. The continent on the other side of the ocean moves closer and closer to the subduction zone. This is how two continents can come together at a subduction zone. Remember that continental lithosphere is much less dense than the mantle. Therefore, continental lithosphere cannot be subducted. The subduction stops. The continent that was coming along toward the subduction zone keeps working its way under the other continent for hundreds of kilometers. This continues until finally the friction between the two continents is so great the plate movement stops. The zone where two continents have met and become welded into a single continent is called the suture zone. There is only one good example on today's Earth. The Indo-Australian plate has collided with the Eurasian plate and is still working its way under it. Right here. Where is my, okay, there we go. There is a good reason why the Tibetan Plateau is the largest area of very high elevations in the world. The continental lithosphere is much thicker there because one continent has moved under another, causing the crust below to buckle and fracture. Figure 4. The Himalayas and the Tibetan Plateau were formed by the collision of the Indo-Australian plate with the Eurasian plate. The Indo-Australian plate is being shoved horizontally underneath the Eurasian plate, so the continental crust in the Himalayas and the Tibetan Plateau is much thicker than normal. Mountains at plate boundaries. Most of the great mountain ranges of the world are located near convergent plate boundaries. There are a number of different mountain ranges on Earth. The Alps in Europe, the Himalayas in southern Asia, the Andes in South America, and the coastal mountain ranges in western North America are some examples. Mountain ranges like those are formed in mainly two ways. You already know that magma that is generated above the subduction plate rises up to form a chain of volcanoes. Much of the magma remains below the surface and cools to form batholiths. Volcanoes at the surface and batholiths deep in the crust add a lot of new rock to the area above the subduction zone. This addition of new rock makes the elevation of the land much higher. Also, many subduction zones experience compression. This occurs when the two plates are pushed together by plate movements elsewhere. In places like that, great masses of rock are pushed together and stacked on top of one another. These stacked masses of rock form high mountains. This also happens where two continents collide with each other, as in the Himalayas. Transform plate boundaries. At transform boundaries, plates slide past one another. The surface along with which the plates slide is called a transform fault. Transform faults connect the offsets along mid-ocean spreading ridges. Most are short, but a few are very long. The most famous transform fault forms the boundary between the North American plate and the Pacific plate in California. It is several hundred kilometers long. You can see from the map in Figure 5 that the San Andreas Fault connects short segments of spreading ridges at its northern and southern ends. The movement along the transform fault is limited to the distance between the two segments of the ridge crest. Figure 6 is a sketch of mid-ocean ridge showing segments of the ridge crest offset by transform faults. Between points 1 and 2, plates A and B are sliding past each other. Earthquakes at plate boundaries. The global distribution of earthquakes and volcanoes is controlled mostly by the movement of Earth's lithospheric plates. Like volcanoes, earthquakes occur where these plates diverge and converge. Earthquakes in ocean basins tend to have a linear distribution along the mid-ocean ridges. Earthquakes occur where new lithospheric plates are created and spread apart. The Mid-Atlantic Ridge of the North Atlantic and South Atlantic Oceans is a classic example. Earthquakes also form along transform faults that form perpendicular to the ridge crests. In continent to continent, ocean to continent, or ocean to ocean collision settings, earthquakes are common. However, in continent to continent settings, there are no Volcanoes. This pattern can be observed along the Himalayan mountain range, which extends for over 1,500 miles between the Indian subcontinent and the Tibetan Plateau. In places, this broad belt of shallow earthquakes reaches a width of 250 miles. Similarly, transform settings are associated with shallow earthquakes, but usually no volcanic activity. Earthquakes in the interior of continents are probably located along ancient faults that become reactivated because of changes in stress across the plate. Plate tectonics. You can now see why the field of study of plate motion is called plate tectonics. Tectonics comes from the Greek word tekton, which means builder. Plate tectonics refers to the building of the features on Earth's surface due to deformation caused by plate movements. You have read that plate movements create mountain ranges, trenches, and rift valleys at or near plate boundaries. Also, there is a clear relationship between volcanoes and plate boundaries. There is also a relationship between earthquakes and plate boundaries. This is particularly evident around the rim of the Pacific Ocean. The subduction of oceanic plates around much of the rim results in volcanic arcs and earthquakes. Tectonics has far-reaching effects on the geosphere. New crust is generated. Most large-scale surface features are related to plate tectonics in some way. In fact, the plate tectonic system is so vast in scale that it operates almost independently from Earth's other major systems.